Part 4 of algebraic structure. If you haven't seen previous parts, watch that first and then come back to this. Fields and ordering. If the elements of a ring, excluding the zero, form an abelian group with the second operation, then it is a field. For example, write the multiplication table of the remainders of division by 5, and you will see that it satisfies all the requirements for a group. You will probably have noticed that the group does not contain the number 5 itself, since 5 equals 0. In a ring, I can say that it is ordered when you have a special subset of that ring behaves in a very special way. Any two elements of that special subset are added or multiplied, their sum and their product are again in the special subset. Take the negative numbers in R. Can they be that special subset? Well, the sum seems to be all right. It is also a negative number. But things don't work with the product. It is positive. What about the positive numbers? Yep, and in fact we call that special subset the set of positive elements. Now, I gave the definition for an ordered ring. I can also define an ordered field the same way. But what does a complete ordered field mean? Well, the definition looks rather nasty. It is complete if every non-empty subset which possesses an upper bound has a least upper bound. I can also turn things around and talk of lower bounds, and of the largest of these, etc., but most of that will be just a mirror image of what we have dealt with so far. So that should be it. And for years that did seem to be it. I seem to have all the numbers I'd ever care to have. There was just one small stick in the works, but most people just sort of pretended not to notice, and that was that not all polynomials had solutions. One simple polynomial of this kind is x2 plus 1 equals 0. It's so simple. Yet there's no self-respecting number that would solve this polynomial. There were these funny answers which seemed like they should be solutions, but no one could make any sense out of them, so they were considered imaginary solutions. Which was really too bad because they were given the name of imaginary numbers, and now that the name stuck we realize that they are numbers just as good as any of the ones we have been using for centuries. And in fact that takes us to the last great pinnacle in this short excursion. The field of complex numbers. I can define an algebraically closed field as a field where every non-constant polynomial, i.e. one with an x in it from high school days, has a 0 in the field. 2. This in short means that as long as the polynomial is not a constant number, which is no fun anyways, but something which looks like it wants a solution, like 5 by 3 minus 2 times 2 plus 6 equals 0, it will always have one, if you are working with complex numbers and not just reals. There is another definition which is probably just as good, but may or may not be easier. A field is algebraically closed if every polynomial splits into linear factors. Linear factors are briefly factors not containing x to any power of 2 or higher, in other words in the form x plus b. For example, x2 plus x minus 6 can be factored as x plus 3, x minus 2. But if we are in the field of real